Chapter 9. The Redeemer. Kneeling beside the second murder victim, Jan Schumann knew something was wrong. She'd written the script, coached the actors, and carried her props into the party, a charity fundraiser in celebration of her 10th year organizing murder mystery parties. There were some 200 people in the room. She'd put the show on for free. She'd raised $1,000 for charity. But as the mystery reached its denouement, she realized she was stuck. She'd felt weakness in her legs before, but she had always chalked it up to the cold. Now she knew it was something else. Her legs were unresponsive. She couldn't get them to move. It was February 1996, and Sherman, then living with her husband and two small children just north of Los Angeles, was quickly losing control of her body. Her neurologist was stumped. He ruled out multiple sclerosis immediately, but he couldn't offer her a diagnosis. He sent her home. I had no explanation for it, she said. I thought it would go away. Doctors at the University of Southern California tested her extensively for multiple sclerosis, performing a spinal tap and a vision test. The results came back negative. When something looks like MS and smells like MS, even though the tests are all negative, we classify it as MS. She recalled the doctors telling her. But, like her primary neurologist, they could not offer her a treatment. They sent her home too. By summer, Sherman could no longer raise her arms to reach the bowls in her kitchen cupboard. Her body was failing fast, and at this rate she believed she'd be dead in a few years. She persuaded her husband to move the family back home to Pittsburgh. At least there, she reasoned, her children would be surrounded by family. Like their colleagues in California, doctors in Pittsburgh ruled out MS, diagnosing her instead with cerebral degeneration, a poorly understood set of symptoms caused by motor neuron death in the spinal cord. It's remarkably rare, an orphan disease. It's not even popular enough to have an association, she said. No one knows what to do. Within 3 years, Sherman had gone from being healthy and active to a wheelchair-bound invalid. She could no longer walk. She had two young children to rear, but she was so weak she needed a motorized wheelchair just to get around. She couldn't feed herself, and she had to be placed on a shower chair for bathing. I wasn't finding any light at the end of the tunnel here, she said. Prozac blunted the suicidal thoughts that accompanied her decline. But now back in Pittsburgh, she was confined to her home. She had already given up her career in volunteer work. She couldn't help clean. She could only attend parent meetings if the school held them in a building with ramps. Their Pittsburgh home had 2 stories, so Sherman slept on the ground floor, only rarely going upstairs to her kids' bedrooms. I wish I could have taught them this is how you fry hamburger. This is how you clean a pot, she said. I miss tucking them in and watching them sleep. Instead, a large portion of any given day for Sherman is consumed by the menial task of maintaining her inanimate body, having a caregiver bathe her, shampoo her, change her clothes, or help her go to the bathroom. One of the idiosyncrasies of Sherman's condition was that while her nervous system was non-functioning, her sensory system remained intact. It wasn't just that she could feel everything. Some parts of her body were hypersensitive. It was painful, for instance, when the skin on her knee was stretched. Her body overheated easily, and it cramped if left too long in one position, often needing minor adjustments. If I had the money, I would hire someone to just scratch me, she said. Sometimes I can use the joystick I push to drive my chair to scratch my nose. But if no one's around and my head is itchy, it just itches. Her condition taught Sherman to give caretakers precise requests. Please move my right hand 2 inches up. Please remove the blanket from my right shoulder. She tried to be what she called a good invalid, grouping her requests so caregivers are not forever ferrying things back and forth to her. Administering sips of water, turning on a fan, or adjusting an arm, every person that goes through this feels guilty for being a burden. People don't treat you like that, but you see the lengths they go to get you ready to go, to strap you in, to get you to the van or whatever, she said. You can't help noticing it. Sherman's guilt wasn't confined to her paid caregivers. She was even more troubled by the emotional toll it took on her family. Her disease at times overshadowed her children's upbringing. It constrained her social life, a source of guilt but Sherman, and a source of despair for her husband, Bob. When she was healthy and we would come back to Pittsburgh, she had a lot of friends. When she came back sick and in a wheelchair, a lot of those friends disappeared, he said. People will say, "Oh, what's your wife doing?" I wouldn't tell them, but every now and then I would get close to someone. I'd mention my wife is quadriplegic, and you could see sometimes they would take an emotional step back. How do you socialize as a couple? Sherman's faith in God had always assured her there was some grander purpose to her illness. But as the disease progressed, God's love felt increasingly distant. By 2011, twin bouts of septic shock had placed her in the hospital. The first nearly killed her. She was convinced the infection would return, increasing in severity. That was the year I was going to die, she said. Sherman was raised Catholic and her entire childhood and had unfolded within a 3-block radius of St. Elizabeth of Hungary. But with its sullen masses and appalling sex scandals, the Catholic Church no longer provided her much comfort. She went to Mass, but only because that's where Bob went. And after 2 rounds of sepsis, her paralysis no longer seemed like part of some larger, mysterious plan. It seemed like an awful genetic fluke. She was desperate, hopeless, and alone. I told my family that the next time I got sick, I didn't want any antibiotics, she said. I was just going to let the infection run its course. Making matters worse, she was lonely after her young child left for college. She had been working with a caregiver to adapt one of her murder mystery parties into a novel, but she abandoned the project when her computer crashed, erasing her work. God felt very far away, and she spent hours each day watching DVDs, listening to audiobooks, or playing up to 40 games of online Scrabble. It was around this time that a friend sent her a video of a thin man in a wheelchair, not unlike her own. Sherman watched as a young man used his brain to move a prosthetic limb, pulling pegs from a board and touching his girlfriend's hand. It was Tim Heames, of course, and it was unlike anything she'd ever seen. Sherman was on a conference call with Schwartz's team at Pitt a few days later, kicking off a months-long procession of psychological and physiological tests. Researchers hooked Sherman up to an EEG machine to test her neural activations. They tested her verbal skills. They placed her in an fMRI machine and had psychologists evaluate her mental stability. 14 years I haven't moved anything below the neck except for spasms. Now I have this chance to move a robotic arm and to advance science, she said. What's the downside of that? There was nothing in me saying, don't do this. So it was that on a chilly morning in February 2012, surgeons implanted twin Utah arrays in Sherman's motor cortex, one above the area associated with hand movement and the other associated with arm movement. The arrays would only penetrate 2 millimeters into the brain, and surgeons counseled that the greatest risk lay in infection. But Sherman wasn't worried. She'd spoken with Heems, who'd undergone a similar operation with no problem. How bad could it be? What she hadn't accounted for was the pain. I woke up with a bad case of buyer's remorse, she said. I'm thinking, oh my God, I just had brain surgery for this. Am I nuts? Why didn't anyone stop me? As people, Tim Heems and Jan Sherman could not have been more different. Whereas Heems has the image of a pit bull tattooed on his neck, blue flames enveloping his forearms and eyebrow piercing. Sherman is given to wearing a red librarian glasses and sweatshirts with plaid insignias. Just like Heems, however, Sherman proved a passionate research subject, meeting with Schwartz and his colleagues a few days after surgery. They were really just there to test the equipment, making sure the electrodes could pick up signals. But Sherman was ready to go. She arrived wearing a pair of mouse ears with a tail coming out from under where her wheelchair seat. I was a lab rat, she said. Everyone in the room chuckled at the corny joke. Everyone, that is, but Schwartz. I said, come on, Andy, this is funny stuff. You should be laughing, Sherman recalled. He said, well, I don't think of you as a lab rat. You're a fellow researcher on this. I see you as a peer. Schwartz had been working with monkeys for nearly 13 years, coaxing them, performing his neural bidding with a mixture of observation and rewards. But with Sherman, he had an articulate partner, one whom he could tell what he wanted. Better yet, she could tell him what she was thinking. There would be no controlling of cursors here. It was time to play the piano. Sherman had always been a namer of things. When she felt guilty early in her sickness for holding people up, she named her legs Charlie and George. Sorry for taking so long, she'd say, but Charlie and George are not cooperating. It just took all of this off my shoulders. Now, as Schwartz plugged her into the APL arm for the first time, Sherman decided its name would be Hector, while she dubbed her twin electrode ports Lewis and Clark. Helping to chart the vast unknown areas of the brain. Just as he'd done with his self-feeding monkey, Schwartz helped Hector under full computer control, recording Sherman's neural activity as she watched the arm move about the workspace. As he recorded her neural activations, he slowly increased Sherman's control, attenuating parts of the signal that would send the arm in the wrong direction. There were giving her training wheels, shaving off errant signals while allowing her correct signals to guide the arm. As Sherman's brain adjusted to the algorithmic interface, the algorithm adjusted to her evolving neural patterns, creating a more efficient union between Sherman's brain and Schwartz's computers. Schwartz never asked Sherman to use a classifier, thinking about making a fist to send the arm to the right or flexing her elbow to make it go left. He also didn't want her to imagine physical details like flexing her tricep to extend Hector forward or contracting her biceps to pull him back. He wanted her to move the arm naturally. And in those first days, Schwartz surrounded the $70 million arm with pillows, almost like boxing bags. You don't want to overthink anything. Just punch the cushion, punch the cushion, punch the cushion. It makes it a lot easier for us to pick up the proper signals, he said. If she's trying to come up with all these complicated strategies and corrections, we can't understand it. The strategy let Schwartz know exactly what Sherman was trying to do. Her intention was transparent. She wasn't trying to break down the movement into confusing muscular actions or correct when Hector reached in the wrong direction. I bet that she would be able to do 3D movement on the first day, he said. It took about an hour into the second day before she was able to do it. Schwartz had never been able to work like this. He had always assumed his monkeys instinctually thought of reaching and grabbing as they controlled their robot arms, but he never knew for sure. And while his monkeys might have achieved levels of control well beyond that of other labs, his work always carried this disclaimer that it was confined to animal models. Other people who have tried this in humans couldn't get anywhere near the kind of performance we got in monkeys. One of their excuses was, well, maybe humans can do the same thing as monkeys, he said. Not only can we do it in humans, but Jan learned incredibly fast. Schwartz had hit his stride as a researcher, but he'd also looked into an enthusiastic research subject. Schwartz was officially aiming for 7 degrees of freedom. 7 would make the study a success. Privately, the researchers were aiming higher. They said our personal goal is 8 degrees of freedom. Sherman recalled, I thought immediately in my mind, okay, my goal is 10. Schwartz had been working for years before he finally managed to achieve stable 3-dimensional wrist control in monkeys. Sherman figured it out in a matter of weeks. She went from 3D control of the arm to 3D control of the arm and wrist within a first month of study. By the end of the second month, she was opening and closing Hector's hand. 60 days in, and they'd already achieved 7 degrees of freedom, the study's stated goal. They had another 10 months to go. After Sherman's caregiver had warmed her hand pillows, placed a knit cap on her head, and wrapped her in a soft fleece blankets, Sherman piloted her wheelchair into the cold winter morning to be loaded into the 20-year-old van she and Bob had modified, he with a wheelchair ramp, she with polka dots on the side. As the van's motor rumbled and its heat struggled to fill the cabin, Sherman lay strapped in her reclining chair, staring at the ceiling as the van rolled down the steep roads of Whitehall Borough toward the University of Pittsburgh Medical Center. Her caregiver, Karina Palco, was driving them into the city, where Sherman was scheduled to test an orthotic for possible use in the study, and later to talk to a spinal cord injury support group. Nestled in a pile of manila folders on the front passenger seat was a stack of bookmarks for as sharp as a cucumber, the murder mystery Sherman, with Palco's help, had resurrected and published on Amazon.com. She planned to talk to the group about the Schwartz study. Maybe she'd give a short plug for her book, but mainly she wanted to emphasize how important it is that people with spinal cord injuries be involved in research, not just for the advancement of science, but also for their own sense of purpose and self-worth. Growing up in Catholic, Sherman was committed to the ideal of service. Hunger had been her main cause, and throughout her life, Sherman had volunteered in canned food drives and soup kitchens. She had always clipped coupons for deals on things like deodorant and soap. And in California, she'd come up with a coupon scheme to help the needy. I had about 20 unopened deodorants, I thought. Well, I don't need all of these, so I put them in a bag and took them to St. Vincent de Paul, she said. Then I started thinking if I had more coupons, I could do so much more. She called her nascent organization the Redeemers, asking other parishioners to bring in their unused coupons. Sherman would then sift through the coupons looking for the best deals. In the morning, she'd stop at the store while taking her kids to school. I would give them each 3 coupons, so there 3 of us would show up at the checkout lane, each of us with 3 cans of vegetables and 3 boxes of cereals and the coupons. After taking the kids to school, she'd stop by the store again, redeeming 3 more coupons. She repeated the drill each afternoon when she picked up the kids. My kids were accomplished coupon shoppers at 4 years old, she said. I was getting canned vegetables and a lot of other things besides deodorant by the time it was all over. Then came the weakness in her legs and the move back to Pittsburgh. My mom pulled out a big vanilla envelope full of receipts from my work at St. Vincent de Paul. I just burst out crying, she said. That's what I missed. I loved being able to do that, make a difference. Chapter 10, Blind Spots. Sherman was back at Schwartz Lab the morning after her meeting with the support group. An assistant sterilized Lewis and Clark with Q-tips and hydrogen peroxide before plugging Sherman into the computer. They were months into the trial then, and Sherman's brown hair was tinged blonde from all the peroxide. Dressed in a sweatshirt and covered in polka dot fleece blanket, she wore a pair of dark 3D glasses as the neuroscientist calibrated her brain with the computer. Hector stood immobile to her right as Sherman watched a monitor mounted on the wall in front of her. The screen showed a virtual Hector, silver with a bluish hue, against a black and white checkerboard background. A red oval appeared in one section of the screen. As a bell rang, the synthesized voice of a woman instructed, "Wrist up, spread." "Uh-oh," one of the graduate students said. "Grasp," the synthetic voice commanded. The virtual Hector was under computer control. Everyone in the room expected the arm to move swiftly toward the red orb, but the simulated arm just sat there, froze like its physical counterpart. "Wrist clockwise," the calibration module continued. "Release." Again, nothing. "It's not running," one of the graduate students said as he peered at a graph of action potentials and tapped on the keyboard. "It would almost have to be the executive, wouldn't it?" "Reset the executive, yes." Brian Wadlinger, a postdoc charged with maintaining the algorithm. "All right, we're going to try this again." "Wrist clockwise, thumb in," the module droned. Again, the virtual Hector just sat there. "I don't understand it," said Wadlinger. "I don't know what's happening," seconded the graduate student. "Grasp," said the calibration module. "Stop," said Wadlinger. "Wrist clockwise," said the module. "Something's got to be running," he said. "Oh," the graduate student barked, slapping a palm to his forehead. "I opened the wrong environment. Here we go." Hunched on their task chairs, the researchers studied the screen, opening new windows and pressing the keys. Everyone else in the room waited. The virtual arm stood still. "Okay, sorry for the technical difficulties," Wadlinger said. "It's fuzzy again," said Sherman. "Here we go," said the graduate student. "Wrist counterclockwise, spread," the woman's voice commanded. Now the virtual Hector moved crisply towards the red oval. "Grasp," it commanded when it reached the target. "Wrist clockwise," the module instructed as a green rectangle appeared in another area of the screen. The arm moved swiftly toward the rectangle, traveling across the screen toward the new target. "Release," the voice commanded. The arm disappeared, re-emerging a few moments later after its starting position. The virtual arm completed this exercise 17 times. Meanwhile, Sherman sat immobile in her chair, staring up at the screen as researchers recorded from her motor cortex. Just as they'd done in initial training sessions, the scientists correlated Sherman's neural activity with the movements of the virtual arm, linking her neural response to specific gestures before giving Sherman control. Her neurons were adjusting to the computer interface. The algorithm was adjusting to her. Once they had their initial decoder, the bell chimed, and the female voice led Sherman through a series of more delicate hand movements, moving the wrists, pinching, and spreading the fingers. The computer still had some control, but Sherman was taking over. The system's training wheels still suppressed input from errant neurons, but they allowed neurons that fired appropriately to drive the arm's movement. The virtual arm had moved steadily under computer control, but Sherman movements were more hesitant as researchers refined the decoder. The scientists still weren't satisfied, and they hunched over their computers to put the finishing touches on the decoder. Sherman, meanwhile, asked Palco to bring her the New York Times Sunday crossword puzzle, dressed in a Winnie the Pooh and Tigger Hospital smock. Palco accompanied Sherman to each of her testing sessions. She was forever alternating between making minor adjustments for Sherman, raising her chair back a few degrees, moving a pillow, and reading a romance novel she'd checked out from the library. Palco took careful notes on the study's progress, and she was quick to anticipate Sherman's needs, producing the crossword puzzle on demand. As Sherman puzzled over 69 down, Schwartz and Wadlinger huddled together over a puzzle of their own, a drift that apparently crept into the arm's movement. It's a difficult problem because the mean is below half height, so that it should be negative, and the firing rates can't be negative, said Schwartz, dressed in khakis and open-collared sweater. So you truncate it, and that's what causes the drift probably, so you need the bias. One way, a crappy way to correct for it is the bias that we've been doing. But there's a better way to do it, and that's using some nonlinear functions. But if it's nonlinear, then you can't balance it in the center. And said Wadlinger, who apparently understood Schwartz's diagnosis, that's the problem. That is the problem, said Schwartz. What that means is that when you try to use the population vector, it won't work very well. You should talk to Steve. He's working on it. You can't just get the new algorithm, said Wadlinger. Well, talk to Steve. There are two problems. One is that, and the other is the limited sample size. A few feet away, Sherman was equally stumped as she peered under the 3D glasses at the Sunday crossword. One more question, guys. Gold compound salt. Is that oxide? AU. What? I know the AU, blank blank. But the researchers were ready to give her full control, and the virtual arm now charted a shaky course towards its target, hovering non-committally before finally hitting the mark. It had taken nearly an hour for Schwartz and other PhDs in the room to build their decoder. But as tedious and error-prone as these exercises were, they were also absolutely necessary to get this level of control. It's one of the major challenges facing neuroprosthetics. Although the Utah array is designed to float with the brain, it simply doesn't shift as readily as the soft custard-like organ it penetrates. An electrode that one day is snuggled against a neuron will be the next be farther away, making action potentials harder to record. A new neuron might have migrated toward the electrode, and that neuron will have different synaptic connections and firing patterns. You end up recording from different neurons every day, said Jennifer Collinger, one of the study's coordinators. Probably one half to two-thirds stay the same from one day to the next. The others are different. So it's not like she has a stable population of neurons. Then there's the variable nature of neurons themselves. Each cell in the motor cortex has a preferred firing direction, but these preferences are fluid. They change from day to day, even from hour to hour. A cell that fired at 80 hertz on Monday will fire at 60 hertz for the same task on Tuesday. The old algorithm is no good and needs to be frequently updated to keep pace with the brain's shifting landscape. This was particularly true in the early days of the study when Sherman's neural population was so unstable researchers sometimes had to calibrate only after 1 hour. We had just to start over, Collinger said. Things would change so dramatically. The implant eventually stabilized, but they still had to calibrate the system daily. No mean felt considering that it takes a bevy of computational wizards about half an hour to build the decoder. It's a big hurdle facing any commercial neuroprosthetic that uses penetrating electrodes. If you can come up with a 5-minute calibration, people would probably be willing to do that, Collinger said. But if you had to go through this whole 20 to 30-minute process that is computationally intensive, that's not going to be a viable device. The calibration raised other, more mysterious questions as well. When they began the study, researchers used Hector to build their decoder. It was tedious but effective, as long as Sherman had only 3 to 4 degrees of control. As they increased Sherman's control, however, something remarkable happened. Though she could easily open and close Hector's hand in free space, the arm would freeze when she tried to grab a plastic cone. Jan, what the hell? You just did it. Schwartz would say, and then we'd say, Jan, close your eyes. Boom! She could close her hand around the cone. As soon as she opened her eyes, she couldn't do it anymore. What the hell is going on? It seems pretty straightforward after all. We grab a thing by extending our arm and adjusting our grip to suit the object. As Hector can attest, we understand those mechanics fairly well. The real question is what happens in the brain. We expect our sense to give us an accurate portrayal of the physical world. We expect that when we open our eyes, we behold the physical world as it actually exists. We learn to expect physical objects to behave in a consistent manner. If we tilt a cup, we expect liquid to pour from it. We expect light to shine from above and a ball to drop at a certain rate. In other words, we expect the world to adhere to specific physical laws. Evolution has hardwired our brains with an intuitive capacity to understand those laws, and that ability, augmented by ongoing experience, enables our brains to make all sorts of predictions about how objects around us will behave. We're able to cross the street safely because our evolutionary inheritance has endowed us with powerful models to accurately predict how long it takes objects to reach us. But biological evolution only goes so far. It never prepared us for large land-based objects that can travel at constant speeds of 70 miles per hour. For that, our inherited internal models must be modified by a lifetime of watching cars whiz by on the interstate. It's this two-pronged approach that allows us to be successful in the world, whether it's crossing the streets or learning to lead a pheasant with a shotgun. But is it really so simple? At the dawn of the 19th century, the Scottish neurologist Charles Bell hinted at the notion that the brain does not directly perceive physical reality. Bell is best known for discovering the nervous system structure of discrete motor and sensory nerves, arguing that specific nerves are sensitivity only to specific stimuli. You can't hear with your fingers, for instance. But Bell took the idea one step further, reasoning that neither bodies nor the images of bodies enter the brain. It is indeed impossible to believe that color can be conveyed along with a nerve, or that a vibration can be retained in the brain, but we can conceive and have reason to believe that an impression is made upon the outward sense when we see, hear, or taste. Our experience of the outside world is not direct, Bell argued. Rather, the outside world bombards us with stimuli, but what we experience is a neural representation of that world. The German physiologist Johannes Peter Müller furthered Bell's line of reasoning when he argued that nerves have specific irritability and specific energies. Müller was grappling with the idea that we can perceive similar sensations from wildly different stimuli. The eye can perceive light, electrical current, and even physical pressure as vision. The immediate objects of our senses are merely particular states induced in the nerves, as felt as sensations. Müller wrote in the 1840 edition of his seminal text, Handbuch der Physiologie. It isn't merely that the brain relies on neural translations to accurately perceive the outside world. Rather, the outside world presents fraudulent stimuli, tricking the peripheral nervous system and causing the brain to perceive a false reality. It doesn't matter whether the neural signals are instigated by pressure, light, or electricity. The brain, we, experience these stimuli as light. The world is not necessarily as it appears. We can't always trust our senses. Our brains can be fooled. This revelation remains something of a parlor trick through much of the 20th century as brain scientists minded the notion that sensory perception worked like an assembly line. Namely, the peripheral nervous system streamed raw data into the brain, which refined the information, pulsing it through a series of higher brain processes until it produced a conscious perception of reality. Take vision. The prevailing 20th century theory was that as light signals bounce off an object, they bombard the retina, a sheet of specialized photoreceptors at the back of the eye. Those specialized retinal cells then go to work on the photons, with specific classes of retinal neurons sensing colors, movements, shapes, lines, shadows, and so on. These retinal neurons translate the information into action potentials that stream along the optic nerve en route to the thalamus, a deep brain structure that acts as a sort of sensory switchboard, routing sensory information to the appropriate cortical regions. In the case of vision, the thalamus directs ocular information to the primary visual cortex. As the visual stream jumps from neuron to neuron, the higher cortical regions synthesize these smaller bits of information. Light, shading lines, and so on into specific features, the precise shape of eyes, the specific color of skin, ultimately perceiving them as immediate conscious reality. But for all the prodigious neural power this model attributed to the cortex, it also viewed the brain as essentially responsive. Its neural architecture at the ready, this complicated neural assembly line would spring to action only when it received input from the peripheral nervous system. No doubt the model made sense. After all, not only does the physical world appear to us as an object, but our perception of that world seems instantaneous, seamless, and often unequivocal. When we see a man walking a golden retriever along a tree-lined street, and we immediately behold the reality of the scene. We bite into a piece of chocolate cake, and we were bombarded by its soft feel and sweet taste. The world and all its stimuli seem to inundate us, their obstinate physical physicality unmistakable. It's an impression that is only reinforced by our motor system, which seems no less fluid. We reach to grab a peach, and we don't think of our chorus of muscles we must first engage. Our hand simply wraps around the fruit, often before we are consciously aware that we've even reached. We are reacting to the world around us, seeing and tasting and feeling objects that appear before us. As intuitive as it sounds, neuroscientists such as David Eagleman and V.S. Ramachandran have recently argued that this stimulus response theory fails to explain even some of our most basic lived experiences. As Eagleman argues, its veracity was challenged in the 1950s when neuroscientists named Donald McKay hypothesized that the primary visual cortex builds internal models to predict information arriving from the optic nerve. Rather than relying on a one-way tract of communication, the brain enlists feedback loops, where higher brain regions exchange information with lower regions. The theory was dramatically bolstered when McKay found 10 times as many input fibers running from the primary visual cortex to the thalamus as there are fibers running from the thalamus to the visual cortex. We've all seen line drawings of a cube like the one below. We stare at it for a moment, and we notice how our perception of the image begins to shift. One moment the front side of the cube appears oriented down and to the left, the next it seems pointed up and to the right. Nothing has physically shifted, and yet we find the image ambiguous. Our eyes, or rather our brain, can't make sense of the visual stimuli, so our perception shifts back and forth. There's a striking point there, says Eagleman in his book Incognito. Nothing has changed on the page, so the change has to be taking place in your brain. If the brain were merely taking in the object stimuli and refining them into conscious experience, we wouldn't be so confused by the 12 straight lines. The object would present itself and the brain would perceive it. But the brain actively constructs vision, using its formidable neural architecture to process incoming stimuli and build consistent models to produce a coherent experience of the objective world. In the example below, simple as it is, the visual stimulus is ambiguous. There are two varying interpretations, and so our brains, unable to decide which is definitive, toggle between the two, perceiving the image downward facing one moment and upward facing the next. But as Eagleman notes, perhaps the best example of the brain actively constructs vision is the blind spot, as we have at the back of our eyes. It's the sort of thing you could go a lifetime and never notice. As indeed Plenty of us did until the 17th century, when the French physicist Edmé Mariotte discovered we have a large blind spot in both of our eyes. If the brain simply processed incoming visual information, then it would stand to reason that we would notice these blind spots. There would be again a large void in our visual field where no incoming information was available. But we don't perceive a hole in our vision. Part of the reason for this is that the blind spot located where the optic nerve attaches to the retina is a different part of each eye, enabling us to cover the visual field with overlapping stereoscopic vision. Even so, close one eye and no gap appears.